Hello, my name is Thibaud Yvonnet and I am a PhD student at the French Institute in Rigault. In this video, I will give you an overview of our work titled Probabilistic Model Checking for Activity Recognition in Medical Serious Games. In this work, we propose a formal approach to analyze patient behavior. We explore the case of patients suffering from dementia-related diseases such as Alzheimer's. When aging, some people may suffer from cognitive loss, progressively leading to a loss of their autonomy. We want to detect this loss in its earlier stage called mild cognitive impairment. For this, we focus on serious games that target different cognitive functions. These games give a limited set of rules, thus, the number of awaited behaviors is limited. To represent this variety of behaviors, we use probabilistic models known as discrete time Markov chains. We use two different model checking frameworks, PRISM and STORM, that accept the same modeling language. Then, we formulate properties which may have a medical interest using probabilistic computation tree logic. Here, we have an example of such a formula where we use two operators, P and X. The corresponding Boolean property is true if a variable y has value 1 in the next state with probability 0.5. Our first model represents a patient playing a game called card game. This game targets the attentional functions. The player has to match the central picture with one of the pictures beneath. The game lasts at most 5 minutes. For each picture, we take into consideration 4 different actions of the players. They can give a good answer, a bad one, no answer for a given amount of time, or they can simply leave the game. In the case of good or bad answer, a smiley, happy or sad, appears on the screen. The first property here checks whether the model patients gather in average and all along their game session more than 30 good responses. This Boolean property involves rewards, which are variables that count the occurrences of an event. Such variables are not really part of the model, since they do not impact the structure nor the behavior of the model. The second property computes the probability for the patients to give only one good answer in a whole game session without quitting the game. As a matter of fact, this formula is not just a PCTL formula, since it has nested operators. You have an operator here, here, and 2 over here. It is a PCTL star formula accepted by PRISM, but not by STORM. Fortunately, this property can be reformulated in STORM using the subset of PCTL star accepted by STORM. This property has an equivalent meaning and uses reward in a way not supported by PRISM. Here are the results. The average number of good answers is, indeed, greater than or equal to 30. This implies that if some patients provide far less good answers, there is a high chance that they do not belong to the modeled type of patients. Both versions of the second property give the same result. As this probability is really low, we can deduce that a patient suffering from mild cognitive impairment, as modeled, should not behave as such. Our second game is the inhibitory control game. As its name says, it targets the inhibitory control function. In this game, a target, a coin, is displayed for a very short time. The player must click on it as fast as possible. But sometimes, instead of a target, a decoy, the beware sign over here, is displayed. In this case, the player must not click on it. For this game, we take into consideration that the players can click on any signals with different speed, fast or slow, or simply not click on it. The first property computes the average accumulation of good answer using the reward feature. The second property computes the probability to perform a good action, that is, to click only when required. In this formula, the variable I over here corresponds to the number of signal occurrences, target, or decoy. Prism offers a feature to automatically increment this variable. This allows to obtain diagrams of the dynamics of the model. Here you can see such a diagram, which gives an overview of the behavior through time. You can see the dynamic of the previous property applied to good and also to bad answers. The game starts with a short training phase with the first 3 signals. In this model, this training phase slightly improves the patient performance at the beginning. And after, the fatigue impairs it. For the first property result, we see that a patient represented by this model will give around 5 or 6 good answers. As previously said, we used 2 platforms, Prism and Storm. This table shows a comparison of their computing times. On most property, Storm is significantly faster than Prism. Should we put Prism aside? The answer is no. Indeed, Prism is slower, but it accepts more complex formulae than Storm. Furthermore, it offers tools such as the Run Experiment 1, which produces diagrams to summarize simulations or model checking experiments. In the case of Storm, it is usually faster and it accepts formulae for probabilities on reward accumulation contrarily to Prism. To conclude, we use a formal probabilistic approach to model the behavior of patients playing serious games. The goal is to help medical doctors in their diagnosis of patients with cognitive problems. We used 2 model checking frameworks, which provide complementary features. Now, we are performing a medical protocol to gather data on real patients. At the end of the protocol, we will analyze the data with the help of medical practitioners. Afterwards, we will calibrate the models, that is, adjust the probabilities on the action, and perform another model checking round to verify that the models behave as expected for different types of patients. In the long term, we intend to integrate this approach into an automatic activity recognition system deployed in medical practice. Thank you for your attention.
Hello, my name is Jens Weber. I'm with the University of Victoria and I'm chairing this session on requirements. And I would like to start by congratulating Thibaud on an excellent talk on a very interesting topic. Thank you very much, Thibaud.
Thank you.
So while I have a few questions, I'm also, of course, inviting everyone to just log their questions in the chat. And I will start with a question that I was looking at the properties that you defined for your model checking, and you said these properties have medical interest. And in the first game, you had these two properties. Were they at all defined by medical domain experts or influenced by medical domain experts? And if they were, or even if they weren't, can you kind of describe the medical interest behind those properties?
So the models and the idea of the properties were developed with some talk with the medical practitioners, and so it can be medical doctors or neuropsychologists. And so the interest was to check the what were the path taken that a patient could take. So if we look back at the first game, so the first game goes to something kind of you would say simple. It is just checking the number of good response for a patient. So this is something that is kind of already done when you're performing some tests. It's just looking at the results of the patient. When looking at the second property, what is interesting for us is kind of the sequence of events. As what would be the more what would be, let me just think about the sentence. Uh, is there a difference between someone who give one good answer at really the beginning of the game, and then afterward has some false answer, or is it would it be different if he has bad answers and then good answers? So yeah, there's this idea of ring having sequence of events that we want to explore in the case of patient monitoring on Surge Games activities.
Great, thank you for that answer. I have an inclination. It's really interesting to follow up, but there's also a question from Sarah. So I'll give that. I'll read that for you first. So Sarah is a great advocate of games, serious or otherwise, and she's asking whether you can give a hint as to the type of cognitive impairment this will help diagnose.
So for this, we have selected several serious games. So in my talk, there's only two serious games, but actually we have four different. So in the code game, it is what we call the attentional functions and the and also the speed, the processing speed of the human brain. So here it will be for well, attention disorders typically. It is for the code game. It is inspired from a test which has the same name, the code test. Then you have the inhibitory control game, which would be more checking for what we call the frontotemporal part of the brain, where you have the control functions. And so here you got inhibitory control. So the inhibitory control is can be damaged, you could say, in different diseases such as Parkinson disease, Parkinson's, and also Alzheimer disease damage this function at some extent. And afterwards, some other games that we have is a game on memorization, working memory to be more precise. So this is a kind of short-term we try to assess. And finally, there is a final game, which is a motivation game. So trying to check if the patient has some apathy issues.
Great, thank you
Did
for
I
that.
answer the?
I think so. I'm not sure if Sarah is here right now. She says in the chat that she's been moved back and forth between the main presentation and the backstage. But I think this is recorded, and she will get your answer. So I'm wondering. So currently, the models and the analysis that you made, they're purely based on the games. They're not actually observing patients playing the
No,
games. Is that correct?
no, they are not yet observing the patients. We are
Right.
performing right now a protocol to do the observation of the patients,
Mhm.
but at the moment of the publication of this paper, we had no observations yet.
So I was wondering how much assumptions on timing actually play into this. So when I look at the first game that you described, for example, where you had the first property, which was very simple, saying, okay, uh, there is an assumption that you get, I think, at least 30 of these right, something like that, if I recall correctly. But there must be a certain assumption about the time that these things happen, because I mean there's only a 5 minute time limit, so they need to choose these cards under a certain assumption, a certain reaction time. Have you based these assumptions on some, I don't know, clinical evidence on what people can do?
So these assumptions were made with a medical practitioner from the hospital with which I'm working. So I participated to a meeting in which I gave some question papers to every practitioner. So it was medical practitioners, nurses, and neuropsychologists. And there were some open and some closed question, and we tried to assess to make some hypotheses based on the tests that were corresponding to each game, what we could what we could expect from the patients.
All right, that's great. Thank you. Do we have another question? No, wait. So I have another question for you. So you described the use of these two tools, Prism and Storm, and
Mhm.
you also described that well, Prism is slower, but it can do more in terms of more expressive properties. But in the first example, you did show that okay, Storm for Storm as well, and you showed that. I was wondering when I looked at this, the Prism property actually had some condition in there saying not quit. The game's not quit. And I didn't see that in the Storm property. Is that something that is kind of falling
Yeah.
off the equivalence
So
bandwagon, so to say?
yeah. So if you look at the storm property, we use only rewards to replace all the different almost all variables, and so there is a reward which is live game reward, and we in this property we ask for this reward to be equal or inferior to zero, which means that
Ah, right,
the patient didn't leave because the reward gets incremented only if the patient leave. So yeah, the reward is basically a boolean, but with this reward to to create this property.
right.
So yeah, we can have some plays with the rewards to try to translate as many properties as possible, but we don't know yet the limit.
Mm. So far for the games, all the games that you have looked at, Storm actually does the job,
Yeah,
right?
yeah,
Yeah,
yeah, and actually it performs better. You would say. As
yeah.
for an example, the inhibition control game met some issues with Prism too too many and so to because of its algorithms for constructing the model, it changes. algorithms. And
There's a quick question. Is the game available? We only have 15 seconds. You can answer. Is the game available? From Sarah.
yes,
Probably not.
most of the games are available.
Oh, they are?
Yeah. There's there. Well,